All right, let's unpack this. So imagine you're trying to teach a robot something complicated. Maybe it's got one of those super dexterous hands and you want it to, I don't know, screw a cap on a bottle or even spin a pen, like really well.
Yeah, and in reinforcement learning, RL, the usual way you do that is by designing something called a reward function.
Right, the reward function. That's basically how you tell the robot, hey, this is good, or nope, that's bad. It's how it learns.
Exactly. That reward signal is, well, it's everything for the agent. It's like its North Star. It's trying to get as much of that reward as possible through, trial and error.
But getting that signal right, that sounds like the hard part.
Oh, it's incredibly hard, especially for complex stuff.
Yeah, the sources you sent over really hammer this home. There was that statistic, something like 92% of RL folks, researchers and practitioners, they're still doing manual trial and error for these rewards.
92%. And get this, even after all that effort, 89% say their designs just aren't optimal. Or worse, they lead to these weird, unintended behaviors.
Ah, the reward hacking thing.
Exactly, reward hacking. The agent finds some, bizarre shortcut to get points without actually doing what you wanted it to do. It's a huge bottleneck, honestly, really holding back progress in areas like, advanced robotics.
So, okay, what if we could flip that script? What if AI could actually design these complex incentives for other AIs?
Well, that's pretty much the core idea behind EUREKA, this fascinating new system we're going to dive into today.
Eureka.
Yeah, it's a really novel approach. It basically takes these incredibly powerful code-generating large language models, LLMs, and uses them to automate this notoriously difficult job of designing reward functions.
And spoiler alert here, the results sound pretty amazing, genuinely eye-opening.
They really are.
So we're going to explore how Eureka actually pulls this off, look at some of its clever design choices, see how well it performed, and maybe touch on the doors it opens up, like new ways for humans and AI to collaborate.
Definitely. It's a really fresh take on a challenge that's been around for a long time in RL.
Okay, so let's start by maybe digging a bit deeper into why this reward design is such a pain point. We said it's a learning signal, but why is it so much harder for, say, a complex robot hand compared to just teaching a robot to walk straight?
Right. Well, think about teaching that robot hand to grasp something fragile, like really gently.
Okay.
You need the fingers to apply just the right pressure. The wrist needs to be angled correctly. The object has to stay stable. It's a lot. Now, if your only reward is, did you grasp the object? Yes, no. Well, that signal's way too sparse.
Meaning the robot might try stuff for ages and never accidentally succeed, so it never gets any positive feedback.
Exactly. It might try a million random things and never even get close enough to the object to learn anything useful, get zero reward over and over.
Right, so you try to shape the reward then, like give it points for getting closer or for touching the object.
Precisely. You try to break it down. Points for finger position, points for approaching, maybe a penalty if it drops it. But then you hit the other big problem. Those unintended consequences, the reward hacking.
Oh, yeah.
What if the robot figures out it can get loads of points just by, wiggling its fingers near the object without ever actually grasping it? Or maybe one part of your carefully crafted reward accidentally discourages a movement that's crucial later on.
I see.
So tuning all those different parts, making sure the weights are right, ensuring they work together without creating loopholes. It's like trying to balance this incredibly complex equation. Even the experts, the human designers, can spend weeks, even months, just tuning the reward for one task. And often, it's still not quite right.
Okay, yeah, that definitely sets the stage for needing a better way. Which brings us to Eureka. It stands for Evolution-Driven Universal Reward Kit for Agent, right? What's the big idea here?
The core idea, and it's pretty audacious, is to just bypass the human programmer entirely for writing that reward function.
Okay.
Instead, you take a powerful coding LLM, the research used GPT-4, and you basically ask it to generate the actual executable Python code for the reward function.
Wait, so the LM isn't just describing the reward in words, it's writing the code that runs in the simulation.
Precisely. The LLM becomes the reward programmer. And the whole Eureka system is designed to let this LM reach human level, sometimes even better than human level performance in generating these functions.
Wow.
And the goal is to automate it, make it work across lots of different tasks, handle really complex things like robot hands, and crucially do it in a way that humans can still, oversee and guide if needed.
Okay, so how does it actually do that? It can't just be asking GPT-4, hey, write me a good reward for pen spinning, surely. The paper mentioned 3 key sort of algorithmic pillars. Let's start with the first one, environment as context.
Right, this is absolutely fundamental. To write code that actually works in a specific simulation, the LLM needs to know what information is available, what variables can it actually use.
Makes sense.
So Eureka doesn't just give it a text description of the task. It gives the LLM access to snippets of the actual source code of this simulation environment.
Ah, so it can see the real variable names like fingertip position or object velocity or whatever's in the code.
Exactly that. Things like fingertip O's, object rotation, joint velocity. There's an automatic script that extracts these relevant bits. And this is key because it allows the LLM to do what they call zero-shot generation of potentially working reward functions.
Zero shot meaning on the first try.
Yeah, potentially. Because it knows the specific variable names and structures it can use in that environment, it can generate executable code right off the bat without needing special prompts or pre-made templates for every single task. Now, obviously, that first attempt might be buggy or just not very effective.
Which leads us right into the second pillar, evolutionary search. So how does it get from a potentially bad first guess to something good?
This is where the evolution-driven part comes in. It's
Yeah.
pretty clever. Eureka doesn't just generate one reward function candidate. In each round or iteration, it samples a bunch of them the paper mentions, using 16 candidates per iteration.
Okay, 16 different reward ideas generated by the LLM. Then what?
Then, it takes each of those 16 generated reward functions and actually uses it. It trains a reinforcement learning agent for a little while using that specific reward code just to see how well the agent performs.
Oh,
Basically testing how fit that reward function is.
So it runs these little mini training experiments for each candidate reward.
Exactly. Then, it looks at the results. The best performing reward functions from that batch of 16 get selected.
The winners.
Right. And the code of those winners is then fed back to the LLM. The LLM is prompted again, but this time it's told, okay, these ones worked well, generate some new variations based on these successful examples. They call it in-context reward mutation.
Ah, it's like natural selection, but for code. Generate variations, test them out, keep the ones that work best, and use those to breed the next generation with some mutations.
That's a perfect analogy. And this whole iterative process, repeating this cycle, turns out to be way more effective than just generating, say, 100 reward functions right at the start and picking the best one.
Why is that?
Because the feedback loop allows for gradual refinement. The research showed performance steadily improving over several iterations, usually peaking around 5 iterations in their experiments. You can really see this clear improvement curve in one of the figures in the paper, figure 5, I think.
Okay, so we've got the LLM seeing the environment code to make initial guesses, context, and then refining those guesses through trial, selection, and mutation, evolution. But how does the LLM get really detailed feedback? Just knowing a reward led to a high score might not be enough, right? That brings us to pillar 3, reward reflection.
Yeah, and this is maybe the secret sauce for making the improvements really targeted. Just knowing the final score, the overall success rate, isn't granular enough for the LLM programmer.
Right.
So the reward functions that Eureka generates are structured intentionally. They often have individual components. Maybe one part rewards getting closer, another part rewards matching orientation, another penalizes jerky movements, things like that. The reward reflection step then generates a detailed textual summary for the LLM. This summary doesn't just report the final score. It describes how well the RL agent actually managed to optimize each individual component of that reward function during its training run. Plus the overall metrics, of course.
Ah, so it's not just this reward got a score of 8 out of 10. It's more like, okay, the getting closer component value increased nicely, but the matching orientation component value stayed flat, suggesting the agent wasn't really optimizing for that part. Or maybe component B's value got huge compared to component C. Maybe it's drowning out the signal.
Precisely. It provides these fine-grained reward improvement signals, as the paper calls them.
Yeah.
This helps the LLM understand why a particular reward function worked well, or maybe more importantly, why it didn't work so well, or where it could be improved.
So the LLM can then do targeted editing.
Exactly. It allows for targeted reward editing. The LLM reads this text-based diagnosis and uses that information to intelligently rewrite specific parts of the reward function's code for the next evolutionary iteration. Appendix G.1 in the paper has some good examples showing how this helps fix things like a reward term being ignored or having the wrong sign.
That makes so much sense. It's like the AI is learning how to debug and improve its own reward code based on performance data. So those three things together, environment context, evolutionary search, and reward reflection, that's the Eureka
Out at
system.
the core of it, yeah.
Okay, let's talk results then. Did this actually work? Did it create better rewards than humans could?
The results are pretty remarkable, honestly. They tested Eureka across a really diverse set of benchmarks, 29 different RL simulation environments.
29, wow.
Yeah, and covering 10 different kinds of robots. You had walking quadrupeds, flying quadcopters, those complex dexterous hands we talked about, robotic arms, a real variety. Appendix B lists them all.
Okay, a broad test suite. So what was the main finding?
The headline result is that Eureka generated reward functions that actually outperformed the rewards designed by expert humans on a striking 83% of those 29 tasks.
83%, that's huge. It beat the human experts most of the time.
Most of the time, yes. And significantly, averaged across all the tasks, the Eureka-generated rewards led to a performance improvement of 52% compared to the human-designed ones when normalized.
52% average improvement. Wow.
Yeah, if you look at their aggregate results chart, Figure 4, Eureka is consistently sitting there at the top. It significantly outperformed not just the human baseline, but also simple sparse rewards and another LLM-based method called L2R.
Why did it do so much better than that other LLM method, L2R?
Well, L2R was a bit more constrained. It tended to use predefined reward templates and specific API calls. Eureka, on the other hand, has the freedom to generate pretty much arbitrary free-form Python code using the variables it discovered directly from the environment context. That extra flexibility and expressiveness seems to be really critical, especially for those super high-dimensional, tricky tasks like dexterous manipulation.
Okay, but here's a really interesting question for me. Did Eureka just find, like, slightly better tuned versions of the same ideas humans had for rewards? Or did it come up with fundamentally different strategies?
This is one of the most surprising and, I think, exciting findings. The research showed that very often the reward functions generated by Eureka had very low, sometimes even negative, correlation with the structure of the human-designed ones.
Negative correlation, meaning it was rewarding things the human thought were bad or penalizing things the human thought were good.
In some cases, yeah, or just weighting things completely differently. Yet these often structurally dissimilar rewards achieved better final task performance. There are some cool visualizations of this in the paper, like Figure 6 and Figure 16 in the appendix.
So what does that suggest?
It strongly suggests that Eureka isn't just finding the optimum within the realm of human intuition about reward design. It seems capable of discovering genuinely novel, sometimes quite counterintuitive principles for what makes an effective reward. It's exploring parts of the reward design space that humans might just miss.
That's fascinating. Like, it found different ways to incentivize the desired outcome.
Exactly. They give a couple of examples in Appendix G2, for instance, with the shadow hand manipulating objects, or a Franco robot opening a cabinet, where Eureka came up with reward structures that look nothing like what the human experts had devised.
And I assume they did ablation studies, like turning off parts of Eureka to see if all three pillars were really needed.
Oh yeah, absolutely. The results were clear. Taking away any one of the core components, especially reward reflection, significantly hurt Eureka's performance. The drop was particularly noticeable on the harder, more complex tasks. That's shown in Figure 14. All three pillars really work together.
Okay, so this system is clearly powerful at designing rewards. Did this new capability unlock anything? Did it allow them to solve a task that was basically impossible before with manual reward design?
Yes, absolutely. The standout example they highlight is teaching a simulated shadow hand that's a very complex five-fingered robotic hand to do dexterous pen spinning.
Pen spinning, like twirling a pen between its fingers.
Exactly. It's a highly dynamic task. It involves continuous changes in contact, really precise finger movements. It was considered extremely challenging, maybe even infeasible, to achieve just by manually engineering a reward function.
Wow. Okay, that's a benchmark people can kind of intuitively grasp the difficulty of. How did Eureka manage that?
It wasn't just Eureka alone. They combined Eureka's reward design capability with a technique called curriculum learning.
Curriculum learning, like starting simpler and getting harder.
Exactly. First, they used Eureka to design a reward function for a slightly simpler prerequisite task, getting the robot hand to reorient the pen to match various random target positions. They trained an initial policy using that Eureka reward.
Okay, so step one, learn to hold and position the pen.
Right. Then, Using the exact same Eureka design reward function, they fine-tuned that initial policy on the much harder task, making the hand follow a sequence of predefined movements or waypoints that actually execute the pen spinning maneuver.
So Eureka designed a reward that was good enough for both the basic positioning and the complex spinning sequence, and the curriculum helped the agent learn incrementally.
Precisely. They found that trying to train the spinning task directly from scratch, even with the Eureka reward, just didn't work. It was too hard. It was the combination Eureka designing an effective reward for both stages, plus the structured curriculum that finally cracked it. Figure 7 in the paper shows this really clearly. The fine-tuning approach succeeding where training from scratch failed.
That's amazing.
And they even showed it could learn multiple different pen spinning styles or configurations this way.
That is an incredibly powerful demonstration, tackling something that had previously stumped people. Now, you mentioned earlier that this isn't necessarily just about replacing human reward designers, but also about collaboration. How does that work?
Yeah, there are a couple of really promising angles here. One is using Eureka to actually improve existing human-written rewards.
How so?
They ran experiments where, instead of starting Eureka's evolutionary process from scratch, just at the context, they initialized it with a reward function that a human expert had already written for that task.
Okay, so giving it a head start based on human expertise, what happened then?
Really interestingly, Eureka consistently generated new reward functions that performed better than either the original human reward or the reward Eureka generated when it started completely from scratch.
Wait, better than both. So human start plus Eureka refinement beat human alone and Eureka alone.
Yes, that's what Figure 8 shows. It's like the combination was synergistic.
That's fascinating. What's the thinking behind why that would happen?
The hypothesis they put forward in the paper is pretty compelling. It suggests that maybe humans are actually quite good at the first step, identifying the relevant pieces of information, the important state variables for a task, like saying, okay, for this task, the distance to the goal and the object's orientation are probably key.
Right, the conceptual part.
Exactly. But then the LLM, guided by the Eureka process, evolution and reflection, might be much better at figuring out the optimal mathematical logic and the precise weighting for combining those variables into an actual high-performing executable reward function. So it's human insight identifying the ingredients and AI optimizing the recipe.
That's a really neat idea. Human intuition plus AI optimization. What was the other collaboration angle you mentioned? Human feedback.
Right, because Eureka uses that reward reflection step where it processes feedback to improve the reward. Well, humans can actually inject their own feedback into that loop.
How? Like typing instructs.
It's exactly. Providing textual feedback. He showed a really cool example of this in Appendix G4. They were training a simulated humanoid robot to run.
Oh, okay.
And they wanted to run with a natural gait, which is kind of subjective, right? So during the Eureka process, a human would watch the robot's current running policy and just type in feedback. Things like, the gait looks a bit stiff, or the knees aren't bending enough, or it looks robotic.
So qualitative natural language feedback about how it looked.
Yes. And Eureka would incorporate that textual feedback into the prompt for generating the next iteration of the reward function. It would try to adjust the reward code to incentivize gaits that address the human's comments.
That's incredible, using natural language to steer the AI's learned behavior towards something subjective like naturalness.
And they actually tested if this worked. They ran a user study. They got 20 people and showed them videos of 2 agents. One trained using the best reward Eureka found automatically, just optimizing for speed or distance, and another trained using Eureka, but with that added human feedback guiding it towards a natural gait.
And what did the users prefer?
The results were pretty clear. Figure 9 shows that 15 out of the 20 users preferred the gait of the agent that had received the human feedback, even though that agent was actually slightly slower than the purely performance-optimized one.
Wow, so people preferred the nicer-looking gait, even at a small cost to raw performance.
Exactly. It really highlights Eureka's potential, not just for maximizing objective metrics, but for actually aligning the AI's behavior with more subtle, subjective human preferences, maybe even safety considerations that are hard to just write down as simple mathematical objective.
That's a really powerful outcome, moving beyond just task completion to, well, task completion in a way we find acceptable or preferable.
Absolutely. It opens up so many possibilities for teaching robots and agents not just what to do, but how to do it in a way that resonates with human values.
Okay, so bringing this deep dive into Eureka towards a close then, what we've seen is it's a pretty breakthrough approach, wouldn't you say? Tackling that really hard problem of reward design.
Definitely. It uses LLMs, guided by this clever combo of evolution and reflection, to automate reward generation.
And it significantly outperforms human experts on average across a wide range of tasks, even enabling things like that complex pen spinning, which was basically off the table before.
Right. And importantly, it's not just about replacing humans. It enables these really interesting collaboration modes, improving human designs, incorporating direct textual feedback.
Which allows for aligning AI behavior with our preferences, not just raw numbers.
Exactly. I think the fundamental takeaway here is just how powerful and general this combination of large language models and evolutionary search seems to be. It worked really well for this complex, open-ended search problem of reward design. It suggests this whole paradigm could be incredibly useful for other tough search and optimization problems, maybe even beyond AI.
Which really leaves us with a fascinating thought to ponder, doesn't it? If AI systems like Eureka can now effectively design the goals, the incentives, the very definition of success for other AIs, and do it in ways that often surpass human experts, sometimes discovering completely novel solutions we wouldn't have even thought of.
Hmm.
What does that imply for all the other areas where we currently rely on human judgment and expertise to define what an optimal outcome even looks like? What kinds of incredible new possibilities, or maybe even unforeseen challenges, does this capability start to open up as AI continues to develop?